Alright, so in this video we're going to be talking about chain rule today. Up until this point, honestly, all the derivatives that you have had, I have set them up so that chain rule was insignificant in those derivatives. But from this point forward, every time you take a derivative, you must apply the chain rule. And this is our chain rule right here. If you have a function that is a composition of functions, which all functions for the most part can be written as a composition of functions, and that composition here is f of g of x, then the derivative is going to be f prime of g of x times g prime of x. So what you're going to have is you are going to have an inside part, and that inside part is this part. That's going to be your inside function, and then f is going to be your outside function. And so, for example, if you had, let's say y is equal to x plus 2 raised to the third power, and you want to find the derivative of this. This can be written as a composition of functions where you have f of x and you have g of x. F of x would be the outside function, which means we're going to have something cubed, and g of x is going to be the inside function, which is the x plus 2. Now, when you compose f of g of x, what that means is that you are taking the g function and putting it into the f function. So if you take this function right here and put it into x for the x cubed, that's going to give you the function right here, x plus 2 raised to the third power. All right, so let's think of this then. We have the inside part, which is this, and you have the outside part, which is the x cubed. So if we think about our composition of functions here, this is our inside and the cube is our outside. So when it says f prime of g of x right here, f prime is the derivative of the outside function. Well, the derivative of the outside function is going to be 3 times that x, or whatever the inside part is, raised to the second power. That is just the power rule using this function right here. Now, that inside part is our x plus 2. So x plus 2 is going to be inside here. All right, so that is this part right here. The derivative of the outside function, the inside part stayed the same. Now we multiply by the derivative of the inside function. Well, the derivative of x plus 2 is 1, and so multiplying by 1 is not going to change our value any. So our derivative is going to be 3x plus 2 squared. And that's the situation that we have been in up until this point. I have arranged it so that the derivative of the inside part on all of our derivatives has been 1. So multiplying by the derivative did not change anything. Now, what if there was a 3 in front of the x, like a 3x plus 2 right here? Well, then you would end up multiplying by 3 out here, because the derivative of 3x plus 2 would be 3. All right, so let's look at this right here. You need to think of all functions as a composition of functions. You will have an outside part of the function, and you will have an inside part of your function. So if you take this problem right here, for example, the inside part is going to be the 4x plus 3. The outside part is x squared, or you can think of it as something squared. So when you take a derivative, you're going to be multiplying the derivative of the outside part, and the derivative of the outside part is going to be 2 times the inside part raised to the first power times the derivative of the inside part. Well, that's going to take us down to 2 times the 4x plus 3 times the 4, which is 8, giving us 32x plus 24. So let's try another example here. All right, so if you have this function right here, the outside function would be 5 times something raised to the 4th power. So if you take the derivative of the outside part, that's going to give you 20 times something raised to the 3rd power. That's the derivative of the outside part. In this first step, the inside part stays the same. And then your last step is to multiply by the derivative of the inside part. Well, the derivative of 3x squared plus 7 is 6x. So putting it all together, that would give you 120x times 3x squared plus 7 raised to the 3rd power. All right, so for getting to multiply by the derivative of the inside part is one of the most common mistakes made in calculus with derivatives. Remember, you must always multiply by the chain. The chain is the derivative of the inside part. It is a rule, and it must be done. So if you don't do it, then you are breaking the rules, and you can be thrown in calculus jail, sentenced to taking derivatives for the rest of your life. And you'll probably get them mostly wrong. All right, so let's take the derivative of this, which this problem is going to involve using product rule because we've got a multiplication here. And so let's start out dy dx. That is going to be the first which is this, times the derivative of the second. Well, the derivative of this is going to be 3 times the inside part raised to the 2nd power. Inside part stays the same. And then you multiply by the derivative of the inside part. All right, so that's first times derivative of the second, plus second times derivative of the first. Well, that's going to be 2 inside part first power. Inside part is 2x plus 3 times the derivative of the inside part, which is 2. All right, so simplifying or putting some of this stuff together here, we've done the calculus really. Now it's just a matter of simplifying things. You have a 3 times an 8x. That's going to give us 24x. And so 24x would usually go out in front. And then we have a 4x squared minus 5 raised to the 2nd power. So now we have plus, we have constants of 2 and 2, so we'll put that together as 4. You have a 4x squared minus 5 and a 2x plus 3. That would be your derivative using the product rule. All right, so now we've got one using quotient rule. All right, so what we're going to do is start out with quotient rule with bottom, which is 6x plus 2 squared times the derivative of the top. Derivative of the top will be 3, inside part, second power, times derivative of the inside part, minus the top times derivative of the bottom, which would be 2 inside part first power, times derivative of the inside part. All of this is over the bottom squared. And when you square this, that brings it up to the fourth power. All right, so we're going to simplify this a little bit. The 3 and the 15 is going to give us the 3 and the 5 is going to give us a 15 for a coefficient. Now, one of the things we'll recognize here is there is a 6x plus 2 in this term. There's a 6x plus 2 in this term. And we have 6x plus 2 down here, which means we can cancel out a 6x plus 2 in each one of those terms. So that's going to leave us with a 6x plus 2 to the first power up here, and a 5x minus 1 to the second power, minus, we got a 12 for a coefficient. The 6x plus 2 cancels all together, so all we're left with is a 5x minus 1 to the third power. And down here, one of the 6x plus 2's canceled, so this is now to the third power. And that is our derivative for that function. So question here is going to be, what is the equation of the line tangent to this graph at x equals 1? What we need for a tangent line is going to be two things. We need to know a point that the tangent line goes through, and we need to know the slope, which is the same thing as the derivative evaluated at that point. All right, so the x-coordinate of this is going to be 1. Y of 1, if you substitute 1 into this, you're going to get 2 minus 1 cubed, which is 1. Now we need to find the derivative. So the derivative is 3 inside part squared, where the inside part is this, times the derivative of the inside part, which is 4x minus 3x squared. All right, so now we need to find the derivative when x is 1. So that's going to give us 3 times 1 squared times 1, which is 3. Therefore, our equation of our tangent line is going to be y minus the y-coordinate of 1 equals m, which is our slope, times x minus the x-coordinate, which is the other one up here. That is your equation of your tangent line. All right, so just so we can get a visual of this, this is what is happening on that particular graph. You've got x value up here at 1, 1. That's your coordinate for your tangent. The red is your function that we had, and this is our equation of our tangent line, 3x minus 2, which is just the slope-intercept form of the equation that we found. So we can see that the tangent is valid at that particular point. All right, so let's take a look at finding the derivative here using function notation. Square root of f of x can be written as f of x raised to the 1/2 power. So we take the derivative, which will give us 1/2 inside part negative 1/2 when you subtract 1 from the exponent. Remember, the inside part stays the same right here, but then you multiply by the derivative of the inside part. And this could be simplified a little bit by making this f prime over 2 square root of f of x. All right, so the next one, what you may notice here is that we have a 2x and we have an f of 2x. This is actually a double chain rule situation. We have an inside part here, and we also have an inside part here. So we're going to have to do chain rule twice. So starting out, the derivative of the outside parts, like peeling away parts of our derivative here. Always start with the outside, and then the inside stays the same. All right, so the derivative of the outside is going to give you 12 inside part third power. Inside part stays the same. Times the derivative of the inside part. All right, so the derivative of f of 2x. There's an outside part and an inside part here. So the derivative would be f prime of the 2x. But then we have times the derivative of the inside part, which would be times 2. Putting this all together, that's going to give us 24 f of 2x raised to the third power times f prime of 2x. That's taking our derivative in function notation. All right, so this is going to be involving quotient rule. So quotient rule is going to be bottom, which is h of 2x, times derivative of the top. So the derivative of the top is going to be g prime of the inside part times the derivative of the inside part, which is 3. So that's bottom times derivative of the top minus top times derivative of the bottom, which is h prime of 2x times derivative of the inside part there, over the bottom squared. And about the only thing that you could do to clean this up a little bit would be to bring the 3 to the front and bring this 2 to the front right here. Other than that, this is done. So let's consider the function y equals 2x squared minus x cubed raised to the third power. Where would the maximums and minimums be located, and how could you determine the maximums and minimums? All right, so with this, one of the things we will have to do is we will have to find the derivative, and the derivative is going to be outside, inside part stays the same, squared, times the derivative of the inside part, which is 4x minus, this is cubed here, minus 9x squared. Now there's going to be something about maximum minimums here that we have not really talked about yet, and so I want to go ahead and do that. And so with a maximum and minimum, one of the things that you're going to have is a horizontal tangent line. And with a horizontal tangent line, your slope is going to be, or your derivative is going to be 0. That's the slope of your tangent line. The same thing with a minimum. You are going to have a horizontal tangent line and the derivative will be 0. Now the other thing to notice here is that if you think about tangent lines on this side, tangent lines would have a positive slope to them. Over here, tangent lines would have a negative slope to them. So not only is your derivative going to be 0 at a maximum, but what happens from your left to the right is that your derivatives are going to change from positive values to negative values. So the first thing that we're going to be doing with our equation then of our derivative is setting this thing equal to 0, because at maximums and minimums our derivatives are equal to 0. All right, so at this point then let's analyze this a little bit. If you look at this constant of 3, that is a positive 3. It's going to have no impact on making this equation equal to 0 because there's no variable here. So we can forget about that for the time being. If you think about this parenthesis right here, this parenthesis is being raised to the second power. What does that tell us? Anything raised to the second power is always going to be positive. So the only other thing it could be is it could be x values that would make that equal to 0. All right, so let's think about x values that are going to make this equal to 0. Well, if you take the 2x squared minus x cubed, set this equal to 0, and factor out an x squared, leaves you with 2 minus x, which means x equals 0 or x equals 2. We can do the same thing with this over here. All right, so that's going to give us 4x minus 3x squared equals 0. You can factor an x out, leaves you with 4 minus 3x, and x values of 0 makes us 0, and so do x values that are 4/3. Alright, so what that means is that our derivative is going to equal 0 at x equals 0, and that was on both of them, so we just write it once, 4/3 and 2. Alright, so let's think about what's happening to our derivatives to the left and to the right of each of those points. And the reason we want to think about what's happening to the derivative on the left and the right of those points is so that we can determine if we're going to have a maximum or if we're going to have a minimum. Because a maximum, what happens is your derivatives change from a positive derivative to a negative derivative to give you a maximum. For minimums, your derivative changes from a negative value to a positive value. All right, so we're going to do what is called a sign chart. The sign chart is going to be done with our derivative. And I'm just going to draw a number line here, put the 3 points where we have derivatives of 0, and that is at x equals 0, 4/3, and 2. All right, so what we want to do is we want to think about what's happening to our derivative value with numbers less than 0. Well, let's go back up here. Numbers that are less than 0, we said are going to make this, because we're squaring it, it's always going to be positive. So no matter what we put in for x, other than 0 and 2, our answer is going to be positive. So if we put negative numbers in, we're going to end up with positive, let me back that up because we're not quite done with that yet. Now we also have to put negative numbers in here for the x value. So what you can do is just pick a negative number that's in this section over here, such as -1. 4 times -1 is -4. -1 squared is 1. And so what you're going to end up with is -4 minus 3, which is -7. That's a negative value. And a positive 3 times a positive number times a negative number will give you a negative value right here. Between 0 and 1, pick a number that it falls in between there. A number that falls in between there would be 1. All right, so if you plug 1 in here, you're going to get a positive number. If you plug 1 in here, you're also going to get a positive number. So therefore, you have a positive times a positive times a positive, which is positive. Now we're going to pick a number that falls in this section. 1 2/3 would fall in this section. Well, putting a 1 2/3 in here will make this positive. 1 2/3 here will make this negative. You could work that out later. And positive times negative is negative. And then we're going to put a number that falls into this section, such as 3. That's going to give you positive times positive, and this is going to be negative once again. So what's happening here then is your derivative is changing from a negative to a positive at 0. That means you're going to have a minimum right here. Here your derivative is changing from a positive value to a negative value. That means you're going from a positive slope to a negative slope, which is going to give you a maximum. And then right here, your slope is negative and then negative again. Since your slope is not changing signs, or your derivative is not changing signs, that means you will not have a maximum or a minimum. Graphically, what's happening here is your graph kind of looks like a cubic graph, where you have a negative slope and then a horizontal tangent, so the slope is 0, and then it's decreasing again, which is a negative slope. So you're not going to have a maximum or a minimum at this point. And so 0, 4/3, and 2, minimum, maximum, none. If we look at our graph, we can see exactly that. At x equals 0, we have a minimum. At x equals 4/3, which is 1 1/3, we have another maximum. And then at x equals 2, we can see it does that little cubic graph thing where it changes concavity.